Power plants constitute industrial facilities dedicated to the generation of electric power. Typical power stations contain one or more generators and rotating machines that converts mechanical power into three-phase electric power. Most power stations in the world burn fossil fuels such as coal, oil, and natural gas to generate electricity. However, there are power plants which make use of cleaner sources such as nuclear power, biogas, and to an increasing amount renewable sources including solar, wind, wave, and hydroelectric. By energy and fuel source: coal thermal power plants, hydroelectric power plants, nuclear power plants, geothermal power plants, biomass power plants, solar thermal electric power plants, wind power plants. By prime mover: steam turbine plants, gas turbine, combined cycle plants. By duty: baseload power plants, peaking power, load following power plants. Based on the primary categorization of power plants, according to the fuel used for their operation, this video continues with a presentation of the various types of power plants. In coal thermal power plants, the heat produced by burning fossil fuel materials is used to boil water and transform it into steam. The steam is then piped through a turbine. The impulses of turbine moves the turbine itself. The steam is condensed and moved into the boiler to repeat the cycle. Rotation of the turbine rotates the generator to produce electricity. The hydroelectric power plants are stations where energy is produced by the force of flowing water. The water moves through turbine connected to a generator that collects the produced energy. The heat is produced by fission in a nuclear reactor, a light water reactor. Directly or indirectly, water vapor, steam, is produced. The pressurized steam is then usually fed to a multi-stage steam turbine. Geothermal power plants produce electricity generated from geothermal energy. Technologies in use include dry steam power plants, flash steam power plants and binary cycle power plants. Biomass thermal energy is produced by burning natural waste and rubbish, such as plants, animal carcasses, and food byproducts. It produces natural gases that provide heat to water and which is in turn transformed into steam, that later will move through a turbine connected to a generator that collects energy. This kind of power plants creates energy by transforming heat and light produced by the sun into electricity. There are two variations. Solar thermal energy power plants. Such plants store the heat of the sun, which transforms water into steam, that moves through turbines connected to a generator that collects energy. Photovoltaic energy power plants. Such plants generate electrical power by directly converting solar radiation into DC electricity. Wind stations are ones that transform wind energy into another useful kind of energy. A wind farm typically consists of approximately 100 of wind turbines connected to an electric power transmission network. All thermal power plants produce waste heat energy as a byproduct of useful electrical energy production. Typically the amount of waste heat energy equals or exceeds the amount of energy converted into useful electricity. The waste heat results in a temperature rise in the surrounding atmosphere. Natural draft wet cooling towers use large hyperboloid chimney-like structures that release the waste heat to the ambient atmosphere through the evaporation of water. In areas with limited water availability, a dry cooling tower or directly air-cooled radiators may be necessary, since the cost or environmental consequences of obtaining water through alternative for evaporative cooling would be prohibitive. According to Global Asset Protection Services GAPS guidelines on earthquake design of buildings, the following structures or infrastructures are of high significance, risk category 4, in the case of an earthquake event. Buildings and other structures designated as essential. Supportive infrastructure such as communication towers, fuel storage tanks, cooling towers, electrical substation structures, and water storage for fire suppression equipment. Buildings and other structures, the failure of which could pose a substantial hazard to the community. Building and structures that are critical to production or where there is interdependency with other facilities. Therefore, power plants are indubitably considered among infrastructure of high significance in the event of an earthquake. Direct damages at the station level are caused due to weaknesses in design and/or construction methods of structural members. They can be classified as follows. Global damages, such as large story drifts, fractures, damages and collapses of walls. Damages in the gravity load resisting system, including columns sway from vertical position, columns fracture, separation of floors and roofs from walls and columns, fracture of connections and supports, and damages of load-bearing walls. Damages in the lateral load-resisting system, including frame lateral displacement and fracture, severe creaks in shear walls, failure in bracings and other lateral load-resisting components. Damages due to P effects. Direct damages at the station level are caused due to weaknesses in design and/or construction methods of structural members. They can be classified as follows: continued. Structural and non-structural elements falling down, including stacks, parapets, suspended ceilings and false ceiling, lighting systems, and building walls. Foundation defects, including cracking, settlement and displacement. Member defects, including local and global damages in members. Other damages, including transmission towers falling down, separation of HV cables from bushings and their collisions to equipment and people, breaking of batteries and thereby acid effusion. Instances of direct damages include failure of some of the structural steel members in transmission towers due to damages in foundations which have been designed inappropriately. Settlement or disruption of transmission line foundations and thereby tilting of towers or extraction of stubs out of concrete. Collapse of external and internal walls in control buildings in spite of soundness of structure. Cable channels disruption and or tilting of control cabinet supports which make the tables useless. Equipment supports disruption in substations such as rupture of bolts and angles, rotation of foundations and rupture of structure support anchor bolts. Collapse of firewalls on transformers. Settlement and cracking in channels and separation of walls from slabs and or extraction of cables from walls. Indirect damages are caused due to the destructive effects of other factors and often make power systems become out of operation. They can be classified into the following two groups. Damages due to direct earthquake factors, such as liquefaction, rock fall and ground settlement, slope sliding, fault creation and ground vertical motion. Damages due to indirect factors, such as falling of distribution poles and or their connections to power transformers and falling of these transformers separately or in a group on buildings, cars, etc. Destruction of bushings and porcelain and angles of structural support due to large vibrations of connected equipment, and settlement, sliding and destruction of foundations supporting equipment such as transformers and thereby damages in equipment. Reduction of effective mass by eliminating dispensable weights such as partitions, external walls and heavy claddings weight of structure as the origin of earthquake load will be reduced. Minimizing the distance between center of mass and center of stiffness and therefore reduction of tensional component of earthquake load. Reduction of structure's fundamental period by reducing mass and increasing stiffness, appropriately and without a considerable increase in earthquake loads. This method is useful for equipment supporting structures, which moves through long vibrations and have adverse effect on equipment leaning on them and is possible by adding extra members such as bracings or enlargement of section size. Fastening of lateral load-resisting elements to each other in order to increase yielding and strength limit in structures with low level of ductility. Since providing high level of ductility is practically difficult, it is possible to reduce demand for ductility by increasing strength. Increasing fundamental period and damping of stiff structures, which without sufficient strength and ductility are subjected to high-frequency vibrations. Isolators can be used to have appropriate behavior in structures. Increasing stiffness, strength, and damping in structures without sufficient ductility or when story drifts or displacements are important. Thus by using pre-stressed bars, EBF and CBF bracings, shear walls and dampers, stiffness and strength of structures will increase and the level of applied loads will decrease, and this would lead to a considerable decrease in displacements. This method is generally used for non-laterally resistant control rooms. Isolation of different structures from each other and use of filler to prevent direct effect of displacements in some members on other equipment. Use of supportive systems to prevent batteries in switch rooms from overturning. Such systems with horizontal and vertical grids prevent the batteries from overturning during reciprocating ground motions in earthquakes. Appropriate fixing of main and auxiliary transformer to their foundations by anchor bolts or rail supports to prevent them from sliding and overturning. Appropriate fixing of distribution line transformers on their respective poles and use of sufficient anchors to prevent secondary damage even after overturning. Site grading and clearing of the area from damages even after overturning. Fixing transmission towers' location to prevent piers from exhibiting sliding motion along slopes. Avoiding rigid and direct connection between equipment and transformer bushings and change of this connection type to flexible shape. Direct damages. These kinds of damages are usually caused because of weak designs. They may take the form of damages in transmission line towers because of weaknesses in foundation design. Damages in equipment support structures because of weaknesses in structure and or foundation design methods or construction procedure problems. Structural damages in substation building or substation peripheral walls. Indirect damages. These kinds of damages are caused by environmental problems and dissimilarity between actual equipment behavior and design assumptions in extraordinary conditions, which can take the form of soil liquefaction at substations, transmission line towers, stone downfall from adjacent mountains and cliffs, falling of transmission towers due to ground sliding, falling and collapse of substations' peripheral walls due to ground sliding, overturning of batteries in control building due to lack of appropriate supports and position of batteries, which will lead to telecommunication systems and PLC cutoff, horizontal displacement of main and auxiliary transformers and therefore disruption of bushings located on them, overturning of transformers from foundations and breaking of bushings and transformers body, damage to all porcelain material, insulator and bushing due to rigid connection between several equipment. Power plants is an integral part of electric power generation and distribution infrastructure and as such are subject to several interdependencies. Such interdependent networks and systems comprising identifiable industries, institutions, including people and procedures, and distribution capabilities that provide a reliable flow of products and services essential to the defense and economic security of a nation, the smooth functioning of governments at all levels, and society as a whole. A disruption in a power generation and distribution network may cause significant ripple effects. The sectors affected by electricity loss are the following: transportation, water supply and wastewater treatment, education, public health, telecommunications, banking and finance, emergency services, government continuity, information systems. Resilience may be defined as the ability of an entity to anticipate, resist, absorb, respond to, adapt to and recover from a disturbance. Due to interdependencies and cascading effects and since absolute protection of a power generation or distribution entity is not attainable, resilience can in fact also be built through citizens and communities and by how they prepare for, and respond to, power outages. Such preparedness could for instance be led by the electricity companies and targeted at the individual and community levels by sharing accountability for response across the official respondents, local officials, community groups, individual citizens, and the electricity companies. The aim is for households to have response strategies that are complemented by resilience measures prepared for, and by, the community. At European level, especially during the last decades, there is an increased number of large-scale blackouts mainly due to shortages, mechanical failures, overuse by consumers, interconnectivity of electricity transmission systems, transnational electricity network failures. 3 historic mass blackouts in Europe: Italy, Switzerland, Austria, Slovenia, Croatia 2003, approximately 56 million affected. Sweden, Denmark 2003, approximately 160,000 affected. Germany, Poland, Belgium, the Netherlands, Luxembourg, France, Portugal, Spain, Greece, the Balkans, Morocco 2006, approximately 15 million affected.